Okay, so let's start. So yesterday we looked at abelian gauge theories, and in particular we looked at electric charges and magnetic charges. So we encountered Dirac monopoles, and then we looked at electric-magnetic duality. So, but towards the end of the lecture, I was moving instead to some non-abelian gauge theory with fields in the joint representation. In particular, this was only part of the Argyres-Seiberg model because that was needed to give some lightning review of Polyakov monopoles. So I remind you that the motivation is that if you embed the U1 gauge theory into some non-abelian gauge theory, which is then spontaneously broken to the abelian gauge theory, we will see that we can find solutions of the equations of motion which have finite energy and are completely smooth, and nevertheless they carry magnetic charges. I mean, they're interesting for us because they carry magnetic charges. Okay, so this is what I'm going to explain in the next half an hour. As I said, there are books about reviews and books about monopoles. This is just a lightning review, but pretend to be complete in my discussion. All right, so I introduced this bosonic Argyres-Seiberg model. So this is a SU2 gauge theory with the field real scalars in the joint representation with this Yang-Mills Lagrangian plus kinetic term for the scalar plus potential term, which takes this form, Mexican peptide, and the potential is minimized when phi takes this diagonal form. Okay, and this breaks the gauge loop SU2 to U1. So next, to find this Polyakov monopoles, we're going to look at static finite energy solutions of the equations of motion. And so I finished my lecture yesterday afternoon by looking at the requirements of finite energy. So if you want finite energy, of course, we want the energy density to go to zero fast enough at spatial infinity so that the integral, which gives the energy, converges. And so if the by knowing how the energy density depends on the gauge field and the matter field phi in the theory, so I'll actually give you the formula later in a few minutes. We see that it contains the sum of squares, and so some of the conclusion that you draw is that one is that electric and magnetic fields have to vanish at infinity, and the covariant derivative of the scalar has to vanish at infinity, and also the potential has to go to a minimum, and in this case, the chosen to be zero at infinity. Okay. So, in particular, phi has to go to this configuration up to a gauge transformation. Okay. So now the solution, this Polyakov monopole solution, is supported by a non-trivial topology of phi. So what do I mean? So let's look at what happens at infinity. So we're going to have a two-sphere S2 infinity at spatial infinity. Okay. If we look at R going to infinity, space is R3, so there is a two-sphere at spatial infinity. And now we have a field phi, which will go to, let's say phi will go to phi infinity, when R goes to infinity. And so the configuration of the scalar field phi at infinity will define a map from the two-sphere at spatial infinity. So again, this is the R3. Oh, this does not look like a sphere. And this is the two-sphere spatial infinity. This is R. Okay. So if I give you the value of the scalar field at spatial infinity, that gives us a map from this two-sphere, especially infinity, into field configurations that minimize the potential, because we need to minimize the potential. So let me call this base M0. So this is the values of phi such that the half trace phi squared is a squared. Okay. So I know since phi is in the joint representation, it's a triplet of SU2, so you can think of it as a vector of SO3. So if you and this condition minimizing the potential just tells you that the norm of the vector is fixed to be A. Okay. So in particular, you pick a rotation inside the gauge group at a given position in space-time. So this direction selected by phi will break SU2 to U1, and in particular we will have, for this manifold, will also be a two-sphere, okay? Because again, I'm looking at, so this phi is, think of it as a vector inside the gauge group, and it has say, a three-vector with a definite norm. Okay, so now the asymptotic value of the scalar field at infinity is a map from a two-sphere, this is spatial, two-sphere, to another two-sphere, which is inside in field space. Okay. But in particular, this map can be topologically non-trivial, and so its topology is characterized by, well, this is speaking a winding number, or more precisely, a degree of the map, which takes value for those who know what I'm talking about in the second homotopy group. And this tells you how many times this this map winds around the two-sphere, especially infinity. Okay? So let me be more explicit. Let's just give an example. So suppose that the scalar field phi at infinity looks like this. So r hat is the unit vector in the radial direction. So okay, so in particular its norm is A, so the field phi at any point at special infinity lives in this manifold, so minimizes the potential, but the orientation of phi in field space is determined by the orientation of R in actual space. Okay? So this has winding number 1. Because as you go once around the two-sphere spatial infinity, which has to do with R, you go once around this two-sphere in field space. Okay. So, and in particular, you can write this as a sigma 3, the field configuration for the vacuum up to a gauge transformation. And let me call this gauge transformation to minus IT to IT, when now T is beta over 2 minus sigma 1 sine phi plus sigma 2 sine phi. Okay. So the field configuration is related. So this field configuration with non-trivial winding number is related to the original constant field configuration for the vacuum by a gauge transformation. So in particular, you can pick a gauge where the scalar field phi infinity looks like this everywhere, but this gauge transformation which rotates to what is called unitary gauge, is singular at theta equal pi. Okay. So sometimes people like to go to this unitary gauge where phi infinity looks like a sigma 3 everywhere, but the price is that you have to introduce a singular gauge transformation. So but let's not do it in the following. Okay. So now the point is that the winding number of phi infinity is equal to the magnetic charge for the U1, the unbroken U1 subgroup of the gauge group. So recall, I mean, at any point in space-time, phi determines a direction inside the gauge group, and that breaks SU2 to some U1 subgroup which goes along the direction of phi. Okay, so in particular, this, yes.
What does it mean that T is this gauge transformation is singular at theta equal pi?
Okay, so I'm using well, this was a side comment, but since you asked, let me explain. So all right, so I started with this field configuration, and I wanted just to make the remark that you can do a gauge transformation that brings it to constant field configuration. But the gauge configuration goes like this, okay? And in particular, so I'm using a spherical coordinate theta, phi, and so on, which are not well defined at the North Pole and the South Pole, okay? So in particular, I mean, phi is not well defined at the North Pole and the South Pole because phi rotates. Okay. So you have to look at what happens at the North Pole and the South Pole. At the North Pole, which is theta equals 0, even though this object is not well defined, there is a theta in front which will take care of it. So it's going to be regular. You can change coordinates and see that it's regular. But if you look at theta equals pi, again, this term is problematic because you're using the coordinate phi, which is ill-defined, and the term in front now is non-zero, and so it's not going to save you. Okay. So this is kind of like similar to the discussion that I had for the Dirac monopole. If you use a single vector potential, it's going to be ill-defined theta equals pi. So it's the same kind of argument. So what I wanted to tell you is that when the number of the scalar field at infinity is actually related and equal to the magnetic charge for the unbroken U1, which now I define in an invariant way as follows. Okay. So recall yesterday, so I had the scalar like this, and then I introduced I expanded F mu in components, the component which was the photon for this unbroken U1, which looked like this. And then some diagonal terms, which were the W bosons, the contributions of the W bosons. Okay. And so, if you specialize this definition to the case of the constant scalar phi, which is the vacuum, it agrees with the definition of the field strength for U1 that I used yesterday. But now this is more general, and in particular, this is going to tell you that, say, if you are, if you pick this choice of the scalar field at infinity, where, say, when you go at r equals infinity in this direction, phi is oriented in this way, and when you go in another direction, phi is oriented in a different way. So the U1 inside the SU2, because you're identifying the rotation on the special sphere with the rotation in field space by this configuration. Now the U1 that you pick depends on the point. So when you are in this direction in field space, so you see here, phi configuration, the field configuration of phi depends on the direction in space. Okay. So, but so for any directions in space, you'll have an unbroken U1, which commutes with the scalar field phi. So again, so this is so this U1. This unbroken U1 varies along the two sphere. And so, okay, so why is why the number of the scalar field correlated with a magnetic charge? So I'm just going to give a heuristic argument to just, suggest that this can possibly be the case. So if you take this scalar field, the configuration for the scalar field at phi equal infinity, like this, and you compute its derivatives, its exterior differential, you'll see that this is non-zero along the two spheres. Okay, so as you move along these two spheres, spatial infinity, phi changes, phi infinity changes, so the derivative is non-zero. Okay. But recall that if we require finite energy, we need the covariant derivative of the scalar to go to 0. And so the covariant derivative of the scalar, which is d minus I a, so we need 0 is d phi infinity minus I a of infinity integrated phi infinity. Okay. So this is a requirement to have a finite energy solution. And so since the derivative of the scalar along the two spheres is non-zero, you also get you also need a non-trivial gauge potential to cancel this derivative. Okay, so this tells you that A infinity is non-zero along the two spheres. And if you actually compute the derivative of the scalar phi infinity, you can actually determine the value of the gauge potential, and you will see that when you go indeed to r goes to infinity, then the U1 part of the gauge loop, the part which is unbroken, has a gauge potential which looks like a Dirac monopole. So I'm not going to derive it now, but it's a simple exercise. You can find this in all the reviews. So the U1 part of the SC2 gauge group, and particularly the U1 part which is unbroken, has a field configuration at infinity which looks like a Dirac monopole, so it will carry magnetic charge. But as we will see, when instead R goes to 0, so we're in the core of our space R3, unlike the Dirac monopole for U1 gauge theory in isolation, which is singular, this is actually going to be regular field configuration. So this is going to be regular thanks to non-abelian degrees of freedom. So the fact that you can embed the U1 theory inside a bigger non-abelian gauge theory allows you to have field configurations which are smooth. Okay, so now let me introduce the Polyakov ansatz. So let me keep this expression here. So essentially what Polyakov did was to construct an ansatz such that indeed at infinity they constructed an ansatz such that at infinity the scalar field looks like this, and the gauge field for SC2 is such that its component along the unbroken U1 looks like a Dirac monopole. And so their ansatz essentially was as follows. So phi looks like r scalar sigma over r squared times a function of a times the radial coordinate, and a is something like epsilon ijk sigma ixj dxk over r squared times 1 minus k, another function of a times the radial coordinate. and I'm possibly missing some factors of 2 here. I didn't check carefully. Okay, so let me make a comment. So first of all, I mean, the structure is kind of similar to what we have here. So we're going to impose a boundary condition such that at infinity the scalar looks like this, and the gauge field looks like a Dirac monopole. And so the other crucial thing is that, like here, so you see that the scalar field at infinity points along a direction in the gauge group, which is determined by the direction in space. And the same is happening here in this ansatz, where phi goes like R scalar sigma. Okay, and similar here you have an epsilon tensor, sigma I xj xk. So what we're going to do is, so what we've done here is identify, or say lock the SC2 space rotations. So this will be the indices of xj, the xk, with SC2 gauge rotations. Okay, which will be the indices for sigma.
Sorry.
Yes.
Do I remember correctly that you were saying that there are no substitutes in substituting SC2 with SO3 in this case?
Here, no, there are no substitutes because everything is in the joint representation. Okay, then
So
different
it's
people
not
might
important that
disagree.
That's not a sphere, that SO3 is not.
Okay, yeah, in that case, you might. I mean, the point is that phi lives in the Lie algebra. So the Lie algebra for SC2 and SC3 is the same. So the whole discussion is exactly the same. Then, okay, if you worry about subtler things like how do you normalize charges and so on, this might play a role. But for the discussion here, since everything is lives in the Lie algebra, we don't have to worry about the distinction.
Sorry?
Yes.
You in the previous class require that this will be a static solution.
Yes.
But I don't understand why, because it is static, A0 has to be 0.
This is just a definition of static as opposed to stationary.
Okay.
So we're gonna have a solution where A0 is non-zero in a second. So wait for 5 minutes and we'll get there. Okay, so this is the ansatz. So this is the ansatz, and now we're gonna impose say boundary conditions. To ensure regularity and finite energy of the solution. Okay. So there are 2 cases. So let me denote this dimensionless combination AR like psi. So first of all, let's look at what happens when psi goes to infinity. So we are at infinity in space. So we have to recover this field configuration for the scalar, and also a configuration which looks like the Dirac monopole for the gauge field. And so if you compare this ansatz with that asymptotic behavior, you see that so you need the h of psi go like psi. Well, let me write it like this. And k of psi here go to 0 because this looks like monopole field configuration already. Okay, so the decays to 0 here are kind of up to exponential correction. So the exponential corrections are like e to the minus mass of the massive field. So we'll go like e to the minus mass of W times R for A, and e to the minus mass of the X field times R for the scalar. So next we have to worry about what happens when psi goes to 0. Because, so see, we're using spherical coordinates which are not well defined at the origin, so we want to make sure that everything is regular there. And if you impose a finite energy, you will see that h of psi has to go to 0 order psi, and k minus 1 k psi minus 1 has to be also order psi. So in fact, even though solving the full equations of motion with these ansatz is quite complicated, I mean, typically nobody knows how to do it except numerically, you can actually solve the equations of motion using these ansatz either for large radius or for small radius. And when you do that, you see that h of psi actually goes like psi squared for small psi, and k of psi minus 1 also go like psi squared. So I did that in Shor's regularity. And in particular, what happens is that psi at psi equals 0, the scalar field goes to 0, and also the gauge field is 0. So you have the full unbroken SC2. At the core of the monopole. So again, to have a regular field configuration, you actually need the full non-abelian structure. Okay, so there was a complaint about the assumption of a static solution. So let's see what happens if we now introduce a different ansatz. So now let's take phi as above and a as above plus some term along dt. So something which looks like r scalar sigma over r squared. So you take r dt. Okay, happier now?
No.
Too bad. So this ansatz was considered by Julia and Z a few years after Croft and Polyakov. And okay, again, if you essentially repeat the same exercises, which I'm not explaining here, you can compute the charges of these field configurations, and you see that this carries both electric and magnetic charges. So this field configuration lead to dyons. Okay. So then once again you can impose regularity and finite energy, and you will put constraints on the asymptotics of this J. So I should mention that at the classical level, the electric charge of the dyons is not quantized, but if you do semi-classical quantization, then you will find that the electric charges are indeed quantized. Okay, so these are just ansatz, but as I said, it's very hard to solve the equations of motion with these ansatz, because the equations of motion are second order and quite complicated, so even with this simple ansatz, nobody knows how to find analytical solutions. But as we will see, there is a simpler, some simplified ansatz where instead of solving the field equations, we can actually solve some first order differential equations, which are easier, and actually find in that case monopoles and dion solutions. So this is what I'm going to do next. Is there a question?
No, when you say it's hard, you mean like you take the ansatz and then you plug in the equation of motion, and you're saying,
and then we try to solve.
alright, maybe I'll try now.
Okay. If you find a solution, let me know. We'll publish a paper.
By we.
Really,
Publish
yes.
the paper.
Sí que vida, ¿no?
I mean, you know, it's a second order differential equation. So.
I
Try.
I think you just say, well, this is some function, and you give it a name, and then.
Yeah, okay, you don't publish a paper. Huh?
Thank you.
Okay, so now let me describe this Bogomolny Cross-Sommerfield or BPS bound. And again, so we'll work with this bosonic Georgi-Glashow model, which for now and for simplicity has vanishing theta angle. I will restore the theta angle at the end. So what we want to do is to compute the energy of such a field configuration. Okay. So in particular, if it's static or stationary like this, the energy will give the mass of the field configuration. So in particular, we'll be able to learn something about the mass of these monopoles and dyons. Okay, so we compute the energy by integrating the energy density T00. So since there is a 1 over g squared in front of everything, let me compute instead the g squared times the energy over g squared times eventually the mass. Okay, so we just use the standard formula for the energy density, which follows from this Lagrangian, and there is a contribution from the square of the electric field, there is another contribution from the square of the magnetic field, then there are kinetic terms for the scalar, and then there is the potential term. Okay, I hope everyone is happy with this formula. So now we manipulate this formula a little bit. So let me first write it down and then explain. So, so here I had squares in EI, BI, DI, phi separately. So let's instead write some mixed squares, something like EI minus sine theta DI phi square plus DI minus cosine theta DI phi squared plus D0 phi squared plus integral d3x of the potential d of phi. And now since so I introduced this these mixed squares, I get some mixed terms which I didn't have here. So I have to cancel them out. So this gives me 2 integral d3x trace sine theta ei di phi plus cosine theta di phi. Okay, so just to complete the square.
Sorry?
Where now theta is just some auxiliary angular variable that I've introduced in my manipulation. Yes.
When did we switch to Euclidean space?
I'm computing the energy. I'm still
That's what I needed. Yeah, sure. Sorry. Excuse me.
Okay. All right. So now I've written this the energy times g squared in this form, and in particular I have a bunch of contributions which are all non-negative. So this term is bigger than or equal to 0. That term bigger than or equal to 0. Same for this square. The potential is also positive negative. And so g squared times the energy is greater than or equal to this final term. Okay? So, and in fact, if I use here, so if you use the equations of motions, they will imply that dI is 0 and dI is also also 0. This is a simple exercise, but physically you would expect that there are no electric and magnetic supersets. Okay. I'm being a bit sloppy here, but if you look at equations of motions, these conditions, these conservation conditions follow. Okay, so now if I use this, the fact that the covariant divergence of the electric and magnetic field is 0, I can pull the derivative outside this expression, and in particular, I can pull them outside of the trace. So I will get ordinary derivatives rather than gauge covariant derivatives. And so what I get is that the lower bound for the energy is 2 times the integral T3x sin theta times the divergence of trace P phi plus the sin theta times the divergence of trace P phi. Okay? So now I'm going to relate this right-hand side to the electric and magnetic charges with respect to the unbroken U1 subgroup. Okay, so in particular, I introduce magnetic charges M and electric charge N. So this again is going to be magnetic charge is going to be equal to the flux for the magnetic field of the unbroken U1, and this is going to be integral. The electric field is the flux of the electric field up to our normalization. I will get back to this normalization in a second. Okay, so then if I use the definition of what the electric and magnetic field for the unbroken U1 are, which were here somewhere below, that will be erased. So you'll see that this is just 1 over 2a integral of trace by ds. Sorry. So we're now, so here, this is the magnetic field for the unbroken U1, and this is the magnetic field in the whole SU2 group. So I have the trace, and recall I had this definition with trace phi divided by 2a for normalization. And now if I do the exercise here, I get this formula, similar formula to the electric flux. Okay, so here I've also, so this is just using the definition of what is the unbroken U1 for the magnetic and electric field. There is a small subtlety here that I'm relating G squared, the coupling of SC2, which appears here, to E squared, which is the coupling for U1. Okay, and if you look at the normalization that we chose, so if I take this Lagrangian and expand it out, say just keeping the U1 parts, you get a term which goes like 1 over G squared F mu nu U1 squared. But in the normalization of for the William gauge theory that I had yesterday, I had let's say I have to compare 1 over G squared F mu nu U1 squared that I get from here, and match it with the normalization that I used yesterday, which is 1 over E squared F mu nu U1 squared. Okay. So that's the reason for this factor of 2. It's just to conform with our normalization. And remember the, sorry, E squared. And this choice was, this normalization that we chose yesterday is such that n is quantized. Okay, so this is just worrying about normalization. So now I'm going to plug these definitions of the magnetic and electric charges into this formula and express the bound for the energy in terms of the electric and magnetic charges. So using those charges, electric and magnetic charges for the unbroken one, I find that the energy is bigger than or equal to A, the level of the scalar field, times, so here I have a sin theta term times the electric charges and cos theta term times the magnetic charge. So here I get A, I mean, if you check the factors, you get sin theta times the electric charge plus cosine theta times the magnetic charge multiplied by 4 pi over E squared. Okay, and this is this bound holds for any value of the angular variable theta, which I just introduced in the manipulation. Okay. So in particular, the stricter bound for the energy is obtained by maximizing the right-hand side. If you maximize the right-hand side, you get that the energy of this field configuration, which is the mass of the dion or monopole, is bigger than or equal to A square root of n squared plus 4 pi over P squared m squared. Okay, so this is when sin theta is n divided by the square root, and cosine theta is n 4 pi over E squared m divided by the square root. Okay, so that's the stricter bound that you can deduce. And this is known as a BPS bound. So the mass of a dion or monopole is bounded from below by a combination which depends on the vacuum excitation value of the scalar field, the electric charge, and the magnetic charge. Okay, and the bound is saturated by saturated, I mean that we get an inequality rather than an inequality like this in the following limits. So first of all, you need lambda to go to 0 because you had we had the scalar field here. I mean, so you see, so to saturate the bound, I have to cancel all these terms here, all these squares, and the potential. Okay, because the right-hand side that I had here was just coming from this last term. So first of all, I need to send the potential energy to 0. So I need lambda to 0. This is called BPS limit. And what is meant by this is that you send the coupling in front of the potential to 0, but you keep the expectation value fixed to A. Okay? Which looks like a bit arbitrary now. But, so fixed. So if you do that, then the potential term vanishes, and then you want also these other squares to vanish, these 3 squares. So you need V0 of phi equal to 0, and then you also need EI equals sin theta di phi, and VI magnetic field is cos theta di phi, where theta is where tangent theta is n over 4 pi over E squared n. So this sin theta and cosine theta is not this formulas. Okay, so now so if you saturate the BPS bound, you get instead, so you see that we've now reduced everything to a system of first order differential equations. So you just get one derivative. Okay, so these are called BPS equations. So this again, so it's a system of first order differential equations, but so they guarantee that you minimize the energy within a topological sector and check that they imply the equations of motion. So they guarantee that you extremize the action. So now, I mean, these BPS equations, since they are first order, they're easier to solve than equations of motion. And in particular, if you plug in the Toft-Polyakov or Giuliasi ansatz, you just get the first order ordinate differential equation in the radial variable, which are easier to solve. So typically people like to focus on these solutions of the BPS equations. And the interesting fact about them is that since they minimize the energy and extremize the action within some sector of topological charges, they will give the leading contributions to the path integral for fixed topological sector. Okay, so maybe just a quick final comment. So if you turn on the theta angle, theta is different from 0, and you repeat the argument, what you have to do is just to replace, in the final result, you just replace this right-hand side here by this combination. The absolute value of the electric charge plus the magnetic charge times the complexified coupling of the U1, where tau U1 is again theta, so U1 divided by 2 pi plus I or pi over P squared U1. And again, if you compare the complexified coupling of the unbroken U1 to the complexified coupling of the whole SU2 group, you will find some factor of 2. Okay, let's not worry too much about it. Okay. So we've seen that the upshot is that the mass of a dion or magnetic monopole is bigger than or equal to A, the value of the value of the scalar field, times N, its electric charge, plus M, the magnetic charge, times the complexified coupling, absolute value squared. And the quality is saturated if and only if you solve this BPS equations. So now this, this BPS bound and the BPS limit that we considered before here might look a bit arbitrary, but we will see that the BPS bound and equations appear very naturally with n equal to supersymmetry. And a theory with n equal to supersymmetry, as I'm going to review in the next hour or so, you have in the vector multiplet, you have not only the gauge field, but also a scalar field in the joint representation, which is a complex field, plus fermions, and then essentially it will fall into the same class of theories which I consider here. And the potential is actually identically 0 along some flat directions. So if you run the same analysis, this BPS limit is guaranteed for sure along these flat directions, and then we'll see that all these conditions just follow from supersymmetry. And also the right-hand side here of the BPS bound will be implied by the supersymmetry algebra. Okay, so let's take 5 minutes break here, and then we move to n equal to. Okay, so let's start with part 2 of the course. So now finally we get to n equal to supersymmetry. I heard that Francisco has already explained a few concepts like multiplets. So if some of the things that I'm going to say, you know everything about it, then I'm boring you, let me know. I will happily skip them. But okay, so let me start from the basics, from the n equal to supersymmetry algebra. In 4 dimensions. Okay, so the supersymmetry algebra looks like this. So because we have n equal to supersymmetry, we're gonna have 2 supercharges. So here alpha will be some you know SL2 index, and I will run from 1 to 2 equal the number of supersymmetry, and then we have the conjugate supercharged T bar, which is dotted spinor and J. Okay, so alpha dot are SF2 times SF2 indices, and I think I'm gonna use conventions where the sigma matrices are 1 sigma working in Lorentzian signature, mostly minus. Anyway, okay, the algebra looks as follows. So first we have the commutator, anti-commutator of a Q and a Q bar. So now we have these indices I and J, which runs over the 2 supercharges. And here on the right hand side, we have 2 sigma mu alpha dot P mu times delta Ij. Okay, again, capital I, capital J are internal indices which tell us which of the 2 supercharges we're dealing with. So then we have the anti-commutator of 2 Qs. And now, so with n equal 1 supersymmetry on the right hand side, you can only get 0 because of antisymmetry, but now, so here we have the epsilon tensor, which is the only object we can construct with alpha and beta downstairs. So now this is going to be this commutator with symmetric, so we can make it. So we can construct an object Z bar Ij, which is antisymmetric. Okay, because this is already antisymmetric, and the left hand side is symmetric. Okay. But since I and J runs from 1 to 2, we can just replace this antisymmetric object with an epsilon tensor times a number, Z bar. And obviously you have a complex conjugate commutator, anti-commutator. Which looks like this. Okay, so this is the n equal to supersymmetry algebra. So note again that the main difference as comparing with n equal 1 is that we have a right hand side in the anticommutator of 2 supercharges, QQ or Q bar. And that we can only construct if we have at least n equal to supersymmetry. So this object Z is called central charge. So it's going to be some conserved charge, and it's going central because it's called central because it commutes with all generators. Of the superalgebra, so it belongs to the center of the superalgebra. Okay, so since it's it commutes with all generators, we can diagonalize it for any irreducible representation. So next we have R symmetry. So recall the R symmetry is an automorphism of the supersymmetry algebra, so some action on the supersymmetry algebra which leaves the form of the algebra invariant. And so here, for n equal to theory, the R symmetry is U2 or the SC2 times U1. it's U2 because we can rotate Q alpha 1 into Q alpha 2. And in particular, the charges Qi will transform with, say, representation of spin 1/2 under SE2 and our charge -1 under this U1. And as a consequence of this commutation relation in the supersymmetry algebra, the central charge Z is going to be a singlet of SE2 and will carry our charge 2. So, as I said, within any multiplet, which is some irreducible representation of the supersymmetry algebra, we can diagonalize Z, the central charge, because it commutes with everything. And in addition, we can use this U1 R symmetry under which Z is charged to bring Z, to rotate Z, which is so maybe I should say Z here is a complex number, but it's transformed with charge 2 under the U1 R symmetry, so we can bring it to be real and positive by U1 R rotation. Okay. So within a multiplet, you can bring Z into real and positive. Okay, so this supersymmetry algebra and R symmetries. Now we're going to describe supermultiplets, which are irreducible representations. So let's first start with massless supermultiplets, massless irreducible representation. So we say pick a frame where P mu, the energy momentum tensor, is E00 E. Okay, since P mu squared is 0. And then we can rewrite the supersymmetry algebra that we have over there. And so the crucial, the non-trivial anti-commutation relation is the following. Is the QQ bar term. So now if I write a matrix in alpha alpha bar indices, it's going to look like this. Just by plugging in sigma matrices times delta ij. Okay. So now note that if we consider alpha equal alpha dot equal 1, we pick out this entry of the matrix, which is 0. And so this tells us that the commutator of Qi1 Q bar I1 dot is 0. Okay. So if you then compute the expectation value, say of this anti-commutator with alpha equal alpha dot equal 1 on a state. Sorry, I should call this state for vertical side. So what we get is the anti-commutator Q1 I Q bar Q bar 1 dot I, which is its complex conjugate. So this is 0 by the supersymmetry algebra, but now since this object, this Q bar supercharge is a Hermitian conjugate of this one, this is just the sum of norm squares, right? Q1 I psi plus Q1 I dagger psi. Okay. So these are norm squares, so they have to be positive. But the supersymmetry algebra tells us that this sum of squares is 0, and so by unitarity we have to impose that Q1 I psi is 0, and also the complex conjugate Q1 I dagger. So for all physical states. So in particular, if we plug it back into the algebra, we can see that the expectation value of the central charge, or all physical states in a massless irreducible representation, is 0. So from now on, we set to 0 the central charge. Let me keep the algebra. So now, okay, so Q1 with index I and Q1 I with index I dagger has to be 0, but we still have the other supercharges Q2I. Okay, so in particular, we can define the following lowering and raising operators. And for AI, it's 1 over square root 2e Q2I, and its complex conjugate AI dagger is 1 over square root 2e I. Okay, so this lowers helicity and U1 are charged, and this AI dagger raises helicity and U1 are charged. Okay. And if we write the supersymmetry algebra in terms of these new oscillators AI and AI dagger, you'll see that it's very simple. It's just AI, AJ, dagger is delta IJ, and all other anti-commutators vanish. Okay. So in particular, so because Q and Q bar are supercharges, A and AI dagger are fermionic, and so we have 2 fermionic lowering operators and 2 fermionic raising operators. Okay, so to build the representation, we start from a vacuum lambda, where lambda denotes the helicity. So these are massless states, so they're characterized by the helicity. And this lowest state is annihilated by all lowering operators. And then we build the other states in the supermultiples by acting with the raising operator. So we start from lambda, then we have the AI dagger of lambda. This will have this will have a helicity lambda plus 1 because AI dagger raises the helicity. And in particular, if this object has U1 R charge R, then the next 2 objects here will have R charge R plus 1. So again, capital I runs from 1 to 2. And if this was a boson, these are fermions, and vice versa, because A is fermionic. And next we can construct 1/2, say, well, the combination where you use A1 dagger, A2 dagger. Let me write it invariantly as follows. And this will have R charge R plus 2. And there is a single one of them. Okay?
Sorry?
Yes.
I'm a little bit confused. The lambda is helicity, right?
Lambda is helicity, yes.
So when you act with AI dagger, you raise the helicity.
Yeah, I raise because this is a 2.
Yeah. But maybe I'm completely off, but I'm just confused by the 1. I was wondering if it should be a half.
That's right. Very good, thank you. So now let's look at massless multiplets, which are built in this way, and will require the helicities to be of all the states in the multiple, let's say, to be between -1 and 1, okay, so to avoid gravitinons and gravitons. So we can start from lambda equals 0 as our vacuum there, and then so we start from 0 plus two objects of helicity 1/2, so fermions, plus helicity 1. Okay, so this is our multiplet, but so if we require CPT as in any unitary Lorentz invariance theory, we have to add the CPT conjugate states, which here looks like -1 plus 2 helicity -1/2 plus helicity 0. Okay. So in this multiplet we have two real scalars, or one complex scalars, two wide fermions, and one massless gauge boson. Okay, so this is the n equal 2 massless vector multiplet. And we can rewrite it in terms of n equal 1 multiplet as an n equal 1 vector plus an n equal 1 chiral in the joint representation. Similarly, you can start with lambda helicity -1/2 for our vacuum, and then we get -1/2 plus twice helicity 0 plus helicity 1/2. So this by itself might be CPT conjugate, but that depends on the representation under which this object transforms. So let me add that anyway. It's CPT conjugate. I will comment again in a second about this. I'll comment about this in a second. Okay, so this multiplet, which is built like this and contains 4 real scalars, so in fact 2 complex scalars and 2 wide fermions, is the n equal 2 massless hyper multiplet. And it decomposes into n equal 1 chiral multiplet plus another n equal 1 chiral in a conjugate representation. Because this is CPT conjugate. So here I'm talking about representation under gauge or global symmetry. Okay. So in fact, if you just look at this object, it looks like, you know, it might be fine, it might be CPT self-conjugate, and that's only true for pseudo-real representations. So that is a half hypermultiplet. But okay, let me not go into that subtlety. You can safely ignore half hypermultiplets. So this is the hyper. Okay, so next we look at n equal 2 massive irreducible representations. So now we'll work in the rest frame. So the frame is mu mass 0, 0. Okay, so in particular, note that this breaks breaks SL2 and SL2, single SL2. Okay, I should say, I mean, it breaks SO4, 1 to SO3. These are complexification. So in particular, this will identify dotted with undotted indices. So from now on, I will not worry about the distinction. So the superalgebra looks as follows. So Q alpha I anticommutator Q beta J dagger is 2m, the mass delta alpha beta delta ij. Anticommutator Q alpha I Q beta J is equal to, as before, to epsilon alpha beta epsilon ij z. So now I brought I rotated z with a u1r to be real and positive. You can repeat the whole analysis which follows without doing that if you wish, but let's do this for simplicity since we can. And then the complex conjugate relation anticommutator to epsilon alpha beta epsilon ij. Is there a question? So now let's rewrite this supersymmetry algebra in a slightly different form. So you can define the following phrasing and lower operator. Let's define A alpha to be 1 alpha Q alpha 1 plus epsilon alpha beta Q2 beta dagger, and similarly A alpha dagger equals the Hermitian conjugate, and then B alpha to be the linear combination with the minus sign. Okay, so now if you write this supersymmetry algebra in terms of these new definitions, you will find that the anticommutator of A alpha, A beta dagger is delta alpha beta mass L plus central charge Z. And the anticommutator of B alpha, B beta dagger is delta alpha beta mass minus central charge Z. And other anticommutators vanish. Okay. So now, if you set alpha equal beta in the first anticommutation relation or the second anticommutation relation, you get a positive semi-definite operator here, something which looks like A dagger plus A dagger A, and similar here. So this implies, since the expected value of the positive semi-definite operator has to be positive, that implies that the mass here is bigger than or equal to minus the central charge from the first relation, and from the second relation is also, you get the other sign. So the bottom line is that the mass is bounded from below by the absolute value of the central charge. If I didn't rotate Z to be real and positive, it would be a complex number, and you would find this relation with the modulus of the complex central charge. Okay. So now this is called BPS bound, because when you specialize it, because it implies the BPS bound that I introduced before for solitons. Okay. So now notice that this bound is a consequence of the supersymmetry algebra. Okay. So next, so there are two cases here to discuss. One is suppose that the mass, suppose that we do not saturate the BPS bound, so the mass is strictly larger than the absolute value of the central charge. So then what we have is we can construct a multiplet, and this is so-called long multiplet, which is obtained by acting with say a dagger alpha e alpha dagger. Okay, so we start again from a state which is annihilated by all lowering operators a alpha and beta alpha, and we build all the states in the magnet by acting with the conjugate raising operators. So this all in all has 16 states, and is also self-conjugate. And okay, we're not going to discuss this multiplet very much. So these 16s are 8 plus 8. 8 bosonic plus 8 fermionic. And this is the long massive vector multiplet. So the other option is that the BPS bound is saturated, so the mass is equal to the absolute value of the central charge. And now this gives rise to short multiplets. Why short? Because if this absolute value is saturated, then one of the two right-hand sides is 0. And so, say if the first right-hand side is 0, then we have to impose that both A alpha and A alpha dagger annihilate all states. So we can only raise the helicity using, the spin using E dagger. So we only have E dagger or so we get fewer states, and in fact, what you get is a total of 4 states, which is 2 plus 2 plus 4 conjugate. If the representation is not pseudo-real. So these are short multiplets, and there are 2 options. So either you have a massive hypermultiplet or the short massive vector multiplet. Okay. So now I should remark that so if you look at the short multiplets, they have a single set of raising operators, either B dagger or A dagger, so they have the same number of degrees of freedom as the massless multiplets. Okay. So let me write down the comment. It's important. Short multiplets have as many degrees of freedom short massive multiplets as massless multiplets. So indeed, if you start from a massless multiplet, like the massless vector or the massless hyper that I described before, you can give them a mass and at the same time keep the multiplet short. Okay. So massless multiplets can gain mass and remain short. Or BPS saturated from now on BPS. Okay. So we'll in the following analysis we'll mostly be dealing with short multiplets, so either massless multiplets or these massive hypermultiplet or a short massive vector multiplet. So if anybody is curious about why is there a distinction between a long massive vector multiplet and a short massive vector multiplet, okay, so you can get a massive vector by the Higgs mechanism, and so here we can do it in one way. So one is the so if you do it supersymmetrically, one way is you start from a so you always start from a massless vector multiplet, but then this can become massive either by eating a massless hypermultiplet or a vector multiplet. Okay, but so if you eat the hypermultiplet, you gain the extra states from the hyper, and you end up here. If instead the Higgs mechanism is due to the vector multiplet itself, okay, so if the massive, so the vector field will eat some scalar fields and become massive, but all the rearrangement happens within the vector multiplet, and so the number of states does not change, and you remain with a short massive vector. Okay, so in the following we will deal with short multiplets. Okay, so now let me let's make a comment on BPS states. So these BPS states will be the heroes of the rest of the course. So they are defined by this, by the fact that they saturate the BPS bound. So their mass is related to the central charge as follows. Okay, so the first comment is that the BPS relation is not affected by continuous deformations. Like changing couplings or moduli or H bar. Okay, so why is that? So if you change the coupling, the moduli, and H bar, you might expect the central charge and the mass to receive corrections, to change. So that indeed happens, but the equality between the mass and the absolute value of the central charge is not affected. And the reason is that if the equality is saturated, then you have a short multiplet, so with say 4 + 4 states. So now suppose that as you turn on couplings or moduli or H bar, you went from this strict equality to a strict inequality. So now when that means that the BPS states is no longer BPS, but if it's no longer BPS, then it's a long multiplet, and this long multiplet has more states. Okay, so these states cannot come out of nowhere. So that tells you that as you change couplings, moduli, and all continuous deformation parameters, the relation remains. So short multiplets remain short. Okay, there is a small caveat that I want to mention. And so the second thing is, the second comment about short multiplets is decay. It's about the decay of BPS states. Okay, so let's consider a BPS state with central charge Z and mass equal absolute value of Z, and let's work in a stress strain. So we want to ask the question: Can this state decay into Yes.
Can instead of long multiplet become short by continuous elimination? Maybe I don't know some degrees of you change the coupling so you're flowing, some degrees of freedom goes away and they rearrange it.
Yes, I mean the long multiplet can decompose and split into two short multiplets. So for instance, I mentioned that you can get this long massive vector multiplet from a Higgs mechanism by eating the massive hybrids. If you send the value to 0, it will split into two massless. Okay, but that will only happen when the masses tend to 0.
Yeah.
Okay, so we have this this object, and we want to ask whether it can decay into, say, two different states at some point. So, okay, so we have two considerations to take into account. So first of all, so these central charges are conserved charge. So if there is a decay from these BPS states into two states, it must be true that the central charge is conserved. So this relation is required. Okay, but now if you use the BPS bound and the fact that this state is actually BPS, we'll see that the mass of the original state, which is absolute value of Z, has to be equal to the absolute value of Z1 plus Z2 by central charge conservation. And then by the triangular inequality, this is greater than or equal to the sum of the absolute values. So here the picture is as follows, and this is Z, and then this can decay into Z1 and Z2. Okay. And now if here we also use again the BPS bound is bigger than or equal to, sorry, what did I got the triangular inequality wrong. Okay. So this is smaller than or equal to the sum of these two absolute values. And by the BPS bound for Z1 and Z2, so we get that the mass of the original state has to be smaller than or equal to the sum of the masses of the decay products. Okay, so right now I'm not assuming that the decay products are BPS. So, but on the other hand, the decay is allowed kinematically only, if the mass of the original state is greater than or equal to the sum of the masses of the final state. Otherwise, the decay cannot take place. So if I put these two bounds together, we see that the decay can happen if and only if the mass of the original state is equal to the total mass of the decay products, and at the same time we want to saturate all the inequalities here, right? So we'll need M1 to be, so this is the value Z, M1 has to be equal to the absolute value of Z1, so the decay product 1 is BPS, and the same is true for M2, equal absolute value of Z2. Okay. And in addition, so by this we have saturated say the first inequality, but we also want to saturate the next inequality, and so we also need that Z, Z1, Z2 are aligned. So the situation is as follows: if this is Z, can have so the BPS state with central charge Z can only decay into two BPS states with central charges Z1 and Z2 when all the central charges are aligned. If the central charges are not aligned, the BPS state cannot decay, so it's stable. Okay, so is this point clear? Because it's going to be important in following. All right, so next we move to Lagrangians for the various multiplex. So I know that Francisco already covered part of this material, so I'm going to be quick. You saw the prepotential, right, Francisco? Yes or no? Yes. So let me be quick. I just set the notation. So we have a massless vector multiplet. As I told you, this let me call the massless n equal 2 vector multiplet psi for reasons that will be clear in the following. And this decomposes into n equal 1 vector multiplet b and n equal 1 chiral phi in the joint representation. So if I look at its on-shell degrees of freedom, there is the gauge boson, the gauge zero, for the n equal 1 vector multiplet, and then the complex scalar, which is the bottom component of this chiral phi, and it's bifermion. Okay, and I'm drawing it like this because if I introduce a U1J subgroup of the SU2 are symmetry such that this J is 2J3, the third generator in this SU2, and R is the generator of U1 R symmetry, then the charges are 1, 0, minus 1, 0, 1, 2. Okay. So this state belongs to the vector n equal 1 vector multiplets, and this state belongs to the n equal 1 chiral phi, which has to be in they all have to be in a joint representation because they sit in the same n equal 2 representation, and it's a vector, so it fits in that joint. Okay, so next I quickly write the Lagrangian using n equal 1 superspace formalism, just to set the notation. So the Yam's Lagrangian is written as follows. So 1 over 4 pi is some normalization factor, imaginary part of tau, where tau again is the complexified coupling, e over 2 pi plus pi 4 pi over g squared. So then tau multiplies the integral over half chiral superspace of W alpha, where W alpha is the gauge in a superfield. Plus there is a kinetic term for the scalar phi, which is an integral of d4 theta by dagger e to the d phi. Okay. And by n equal 2 supersymmetry, the kinetic terms of the n equal 1 vector and the n equal 1 chiral are related, so they have a single coupling constant coefficient in front. And this is equal in component to Maxwell, sorry, Yam's term, plus the angle term. Plus kinetic term for the scalar. And using also auxiliary field, we have the auxiliary field D in the n equal 1 vector multiplet, so it comes with a D term squared. Then there is 1 over g squared D indicator of phi by dagger coming from here. And then this chiral also contains an auxiliary field, the complex scalar F. So it goes like this, plus fermions, which are not bothered to write. This is quite possibly up to factors of 2. And the trace is in the fundamental representation. Okay, so here I've used n equal 1 superspace formalism for this integral. But there is, in fact, for the n equal 2 vector multiplet, there is an n equal 2 superspace. Did Francisco mention that? Yes or no? Okay, so let me just mention that we can have, for the vector multiplet, an n equal 2 superspace, where in addition to the coordinates theta and theta bar associated to the first supercharges, you also have some theta tilde and theta bar for the second supercharge. Okay, and the n equal 2 vector, what I call the n equal 2 vector multiplet, is chiral in this n equal 2 superspace. So that means that it's annihilated. So let me call this psi here. So now psi is n equal 2 superfield such that t bar alpha dot psi is 0. So it's chiral with respect to the first supersymmetry, but it's also chiral with respect to the second supersymmetry. So in particular, you can expand the n equal 2 chiral in the same way that you expand the n equal 1 chiral in components. So this will look like, so let's expand using the theta tilde. So you get some field phi, which is a function of y tilde theta tilde plus square root 2 theta tilde alpha w alpha y tilde theta tilde plus theta tilde square and psi f of y tilde theta tilde. So this is similarly to the expansion of n equal 1 chiral in component, where now y tilde is mu is x mu plus I theta sigma mu theta bar plus the same with the theta tilde, the second pair of Grassmann coordinates. Okay, just by the same argument that you use in n equal 1 supersymmetry. And okay, there is a where now, I mean, this object is an n equal 1 chiral. Sorry, it's back to theta. So this object is, because psi is chiral with respect to both supercharges, each of the components have to be chiral with respect to the other supercharge. So in particular, the bottom component is nothing but the superfield for this chiral n equal 1 chiral phi. The second component, which is a fermionic chiral superfield, is W alpha superfield. And the auxiliary field is a bit more complicated. Well, it's more complicated, don't ask me too much about it. But it's an auxiliary field and it's determined in terms of phi W alpha and the vector V. And it can be worked out to be as follows. So it's phi dagger of y tilde minus I theta sigma theta bar and e to the v of y tilde minus I theta sigma theta bar theta bar. And out of this you only take the theta bar component. Okay, it's just some complicated expression which depends, which is nothing, which is depends on phi and the vector. So if you use this n equal to superfield psi, which contains all the degrees of freedom of the n equal to vector multiples of v and phi, you can write the Lagrangian, the Wolian Lagrangian as an integral over chiral half superspace, similar to this integral. So you have something like 1 over 4 pi, imaginary part of integral over d2 theta, d2 into theta tilde, but no theta bar tilde, of 1/2 tau psi squared. Okay. So this is quadratic for renormalizability, and if you plug in this expansion, you should reproduce the original form. So the nice thing is that this is manifestly n equal to supersymmetric. Okay, and in particular, in the same way as you can write an n equal 1 supersymmetric chiral term by with a superpotential where you have an integral d2 theta times some holomorphic function w of phi, and this is manifestly n equal 1 supersymmetric. Now you can generalize this formula to an integral over chiral n equal to superspace d2 theta tilde times some holomorphic function, some unspecified holomorphic function of the n equal to chiral superfield, which is n equal to vector multiply. Okay. So in particular, this tells you that the most general Lagrangian for n equal to vector multiplet is determined by, can be written in this form, and so it's determined by a single holomorphic function f of psi, which is called prepotential. So this is holomorphic. And so obviously in the classical case, the prepotential was just 1/2 tau psi squared. Okay, so notice also that by the structure of this Lagrangian, we know that the R charge, the U1 R charge of the prepotential has to be equal to 4, much like the R charge of the superpotential is equal to 2. Now it's 4 because I have d2 theta bar. And also F is an SC2R singlet. Okay. So this is not surprising because phi was an SC2R singlet. So in particular J equals 1. Okay, so in particular, I believe that Francisco has already explained to you, so let me just mention this in passing. Okay, so you can, if you consider generic prepotential here, you can expand this general action in terms of d2 theta, d2 theta tilde, and write the most general n equal to Lagrangian for n equal to vector multiplet in a form like this, where now instead of having the canonically normalized kinetic term for the chiral and the canonically normalized kinetic term for the vector multiplet, you have a non-trivial Kähler potential and a non-trivial coupling matrix here. But because of n equal to supersymmetry, both the Kähler potential, which determines the kinetic term for phi, and the gauge coupling matrix, which determines the kinetic term for W alpha, will follow from F. Okay, I will just give the explicit formula for the case of abelian vector multiplets later, tomorrow. So, but the point is that by n equal to supersymmetry, this term and that term are related, and so in particular, even if the Lagrangian is general, it's not the classical one. It's still true that the kinetic action for the chiral and the kinetic action for the vector multiplet are related. Okay, so let me take just 5 more minutes to write the same thing for a hyper. So if you have a hypermultiplet H, can be decomposed into two chiral, a chiral Q, and say an anti-chiral Q tilde dagger, which is transformed into some representation. So now these are chiral multiplets. I use Q and Q tilde for quarks for traditional reasons. So these are not the supercharges. I hope you're not confused with the notation. Sorry for that. And again, the degrees of freedom, the on-shell degrees of freedom are as follows. Dagger, where again J R equal to 1, 0, minus 1, minus 1, 0, 1. So these are, so psi are bifermions and Q tilde are scalars. So these objects belong to the n equal 1 chiral Q, and these other objects belong to the n equal 1 anti-chiral Q tilde dagger. So Q and Q tilde have to transform in conjugate representations because Q and Q tilde dagger transform in the same representation. So this is just a pair of chirals, Q tilde, in conjugate representations of the gauge symmetry group and global symmetry group. And the Lagrangian, the n equal 2 Lagrangian for hypermultiplet, again written in n equal 1 notation, as a kinetic term. So now let me consider several copies of hypermultiplets with H, I'll use index I. So you have a kinetic term for the chiral Q, similarly kinetic term for Q tilde, and then you can also have an n equal 1 superpotential, which however is constrained by n equal 2 supersymmetry. Plus Hermitian conjugate. So just a few comments. So by n equal 2 supersymmetry, the kinetic term and the superpotential term have to be related. Okay, essentially because B and phi belong to the same n equal 2 multiplet, and so that's the reason why that essentially fixes the superpotential to be Q tilde phi Q. So this restricts, n equal 2 restricts the superpotential to be, and now, okay, let me be explicit with all indices. So if A and B are gauge indices now, let me be explicit about contractions. So we would have Q tilde IA, phi AB, phi is in the joint representation, Q BI. And similarly, you can have the mass matrix, which, I mean, in principle, you might have a mass matrix of this form. So if you write it in this form, the role of of m, the mass is the same as the role played by phi. Okay, so phi here was a scalar in a dynamical vector multiplet, and now you can view m as a scalar in a non-dynamical vector multiplet. So this is for the gauge symmetry. So this is a dynamical scalar. And you can also view the mass parameter as a complex scalar in a vector multiplet for a global symmetry. So this is some external. So you can view this as a scalar in an external vector multiplet. And then SU2R symmetry will actually require that the max matrix M commutes with this complex conjugate. So in particular, you can diagonalize M diagonal of I, and therefore you can write the superpotential term like that. Okay, so but it's going to be crucial that M appears in the Lagrangian on the same footing as phi, so it secretly belongs to some vector multiplet, which however is not dynamical. Okay, and also maybe, okay, the final comment is that essentially the mass of a hypermultiplet, so the effective mass of a hypermultiplet, will come from the second derivative of the superpotential. So you get the term from here and the term from there. And so let me just quickly close by saying that the effective complex mass, so this is complex, so this is a superpotential mass, is essentially, roughly speaking, it's given by the mass m here plus the expectation value of phi, okay, just by taking the second derivative of the superpotential. Okay, here I'm schematic, I'm not writing indices and so on. So I told you that this describes a massive hypermultiplex. I told you that the massive hypermultiplex is BPS saturated, and indeed this complex mass which appears in the superpotential is the central charge. So it's the effective central charge. This effective superpotential mass is equal to the effective central charge. Okay. Final comment, there is an n equal 2 superspace formalism for hypermultiplets, but it's quite complicated and I don't even understand it, so it's not that useful for the following. We'll content ourselves with this n equal 1 description. Okay, so let me stop here and we'll start tomorrow by describing the modular spaces of these theories.